0, tangent of 0. Okay, what's tangent of 0? Go back to pre-cal. Did y'all take pre-cal? Yeah, y'all took pre-cal, right? Looks like this. Has asymptotes at pi over 2 and negative pi over 2. And then it's periodic. It keeps repeating itself. That look familiar? Yeah. That's what tangent looks like. So at 0, tangent of 0 is 0. So you do, in fact, get 0 on top, and then on the bottom, sine of 0, 0. We've been through that already. So we do have 0 of 0, right? So let's start ripping everything apart, okay? Let's see how much I can do in one step here. I don't want to go too far, but at the same time, see if you can handle this. What, by definition, tangent is which trig function over which trig function? Sine over cosine, right? Tangent is sine over cosine. So watch how I rewrite this, and you just tell me whether or not you agree. If you have any issues or questions, let me know. I'm going to write sine pi x over 1 times 1 over cosine of pi x times 1 over sine of 4x. Yeah? Those two over there, if you put those two together, you get sine over cosine, right? You get tangent of pi x there. And then this is just the sine of 4x on the bottom. So that's completely pulled apart, right? Where's the issue? What is causing the problem? What's causing the problem? The last one, good. Yeah, so this is not a problem, right? You get 0 over 1, that's 0, okay? What's cosine of 0? 1, you need to know that. It should be that fast. Cosine of 0 is 1. So this is 1 over 1, that's not a problem. Here, 1 over 0, that's the problem. So I need to fix it. How am I going to fix that?
Add a 4x on top.
4x, we need a 4x on the top of it, don't we? But we can't just throw a 4x on top. We can only multiply by 1, right? So I'm going to multiply this by 4x over 4x, right? That will fix the problem, but at the same time, it's going to create a problem, right? So I fix it, I'm going to drop that 4x over here, but now this is an issue. Can I use the other parts of the problem to resolve the 4x problem on the bottom? Should I write the next line of where we are or no? We have limit x goes to 0, sine of pi x over 1 times 1 over cosine pi x times, now I slid that 4x on top of the sine of 4x, and then times, I still have a 1 over 4x here, right? So that's now the new issue, that division by 0 right there. So what do you think? What can I do? Go ahead. Good. So we're going to use this x right here. We're going to pop it underneath this sign. But then we'll need a pi with it, right? Basically, we need a pi x right here. If we have a pi x right here, then that'll go to 1. But really what we're trying to do is we're trying to find a home for this x so it doesn't cause division by 0. That's what we're trying to do. So we multiply here by pi over pi. And then what I'm going to do is I'm going to say, hey, look, this pi and this x, because it's multiplication, all of that can get pushed underneath that. So now this equals limit x goes to 0, sine pi x over pi x times 4x over sine 4x times, okay, what's still over here? 1/4 and pi over 1, or pi, right?
Did you leave out the cosine function?
I don't know why I left the cosine function. No, I didn't.
Okay.
Maybe you're just tired, you're not able to see right now. It's right here.
All right.
Yeah, no, I forgot to put it there. This right here. It doesn't matter where it is, multiplication, but I did forget it.
Once we know a certain piece of the function is 1, can we just start throwing it out and clean up our mess? Or
Yeah, if you, like this piece right here,
Yeah, I know
if you knew it was 1, then you could just figure out what everything else is doing.
Yeah.
just make sure that on your notation's right, because you don't want to just have it vanish. Like mine just vanished, that's wrong.
Yeah.
It doesn't, but you can focus all of your attention on everything else.
Okay.
Just make sure you bring it, if you're going to say this line is equal to this line is equal to this line, you need to bring it the whole time.
Okay. I can't just start calling it 1 and throw it
Not
in
until you
one
take the
after?
limit.
Okay. Gotcha.
Yeah.
All right.
All right. I think this covers everything. This solves all our issues, doesn't it? This is going to go to 1. 1, 1/4, pi, 1. Right? Pi over 4. Which is what we would have got if we had just seen, right, pi over 4 again. But I hope you all understand there's a huge difference, right? There's a canyon of space between the student who can do this and the student who just says, oh, I've seen this before, the answer is pi over 4 without doing any work. It's a huge difference between those two students, right? I want you to be able to do this because this is more advanced thinking, which I think you need, right, for your major. Let's see. Let's do that one.
So when you said that it doesn't always end up the same, it does, just the way that we get there is different.
No, there's times when it will give you something else.
Definition, but
Yeah, it will. Now, I know that would be a nice way to check your work, like, okay, I got the answer, that's great, but you just need to actually do this to make sure. Let's do, I don't know, which one of those do you want to do? I think B and C are two.
Let's do F.
F, we'll do F, yeah. Yeah, let's do F. Let's do E first. E is real straightforward. Like, it's not that bad. It's sine squared t over t. Notice we're using t, not x, right? Just a dummy variable. So as t goes to 0, by the way, when we write sine squared t, since this is going to come up a lot in this class, everyone needs to be absolutely clear that you understand that that really means the sine function, sine of t, and then square that answer. That's what that notation means. So if we have sine squared t on top, if you let t go to 0, you do sine of 0 first and then square it. But sine of 0 is 0. So 0 squared is still 0. We get 0 over 0? Yeah, that? Okay. So do we have this formula right now? Is it sine junk over junk? The junk's exactly the same. The junk's going to 0? Do we?
No.
We don't have sine, we have sine squared. It's not the same thing, is it? So you can't just say, oh yeah, this is going to be 1. But you can do this. Does anyone know what I'm about to do? Split it. Exactly. I'm going to write sine t, I can do it this way, over t times sine t over 1. Isn't that the same thing? Sine squared on top means sine t times itself. So I just wrote it sine t next to sine t. And ripped it apart a little bit, and now this goes where? If I take this limit. That goes to 1 because I've sine of junk over junk. The junk matches, the junk goes to 0, right? But what about the other one? Times 0 over 1, right? When I take the limit, and that's just going to be 0. So your answer is 0 here. Yes?
So if it's like cosine or tangent, like any of the trig functions of jump to jump, is it always going to be?
No, it's only sine.
Only.
It's only sine. So if you have cosine junk over junk, that's not 1. Good question. All right, now let's do the next one. Next one was the F one. All right, limit x goes to pi over 4. Okay, so that's already a problem. And then we have 1 minus tangent x over sine x minus cosine x. Okay, before we do this one, the big note for today was this, right? There's one more of these that you need to know, but it's not as You don't see it as frequently as this one, all right? The other one is this. If you have limit, doesn't matter what it is, going to doesn't matter. If you have cosine junk minus 1 over junk. I didn't give myself enough room here. Cosine junk minus 1 on the top. So see the difference? This is sine junk over junk. This answer is 1. This is cosine of junk minus 1 over junk. This answer is 0. Now it's in your notes, okay? I put it in your notes here, but it just looks a little different. You see that right there, number 2? So imagine this formula, number 2, but replace the x with junk. So cosine of junk over junk, this answer will be 0 so long as the junk goes to 0 and the junk matches. That makes sense to you? You have to take that on faith. I'm not proving that to you. You're going to take it on faith? Okay. All right. Just in case. I don't think we need it for this one, but just in case we do, I want that. Those are the only 2, okay? And I even say on there, know these 2, all right? Know these 2 formulas. All right, so let's just check first what's going on here. Pi over 4. You're going to need to know what's happening. Well, let's start with the bottom. Sine of pi over 4, cosine of pi over 4. Do y'all know what that is?
It's root 2 over 2.
Root 2 over 2?
Root 2 over 2.
Good. So there's all different ways that you all came from pre-cal, how you understand your trig functions. When it comes to sine and cosine, I always like to think of the unit circle. And when you're at pi over 4, that's this angle right here, right? That's pi over 4. And this has an ordered pair that you need to have memorized. It is root 2 over 2, root 2 over 2. And sine is always the, which coordinate? The y coordinate. So this is sine of pi over 4, and this is cosine of pi over 4. So they're the same. So this is root 2 over 2. This is root 2 over 2. You subtract, you get 0. Now, if you don't know how to read a unit circle and do this quickly, come to my office hours. I know that in pre-cal, a lot of times this is taught in a way that students they make it more complicated than it has to be. So please come by. We'll spend 30 minutes going over how to do a unit circle and get it kind of burnt into your brain. So that's that, right? So the bottom is 0. What about the top? Do we know what tangent of pi over 4 is? 1. How do we get that? Tangent is sine over cosine, right? So it's the y coordinate divided by the x coordinate. So it's 1. So we get 1 minus 1 on top, that's 0. So we do get 0 over 0. So if you don't know any of those trig values, it's going to slow you down quite a bit, right? And you do not want to be pulling your calculator out and doing sine of pi over 4. Like, you want to be past that. So if you're not there, it's okay, but you need to get there quickly, all right? So come get help. All right, so we have 0, 0. What the hell are we going to do here? Notice that we don't have multiplication, right? So I can't rip apart the way I've been ripping apart because these are not factors, these are terms separated by addition and subtraction, right? You'll see it's not going to be as clean like this. I just pull these 2 factors apart. All right, so when you start to get into trouble, all right, one of the kind of rules of thumb is to just rewrite everything in terms of sine and cosine, all right? So I'm going to rewrite this limit. X goes to pi over 4. So the rule of thumb is that I'm going to rewrite everything in terms of sine and cosine. So I'm rewriting the tangent as sine over cosine. Down here, sine x minus cosine x. Okay? That okay with you? All right. What now? Go ahead. What?
Would it be a good idea to turn the 1 into like sine x over sine x?
If you wanted to, you could turn this into sine x over sine x if you wanted to. But you could turn it into anything you want, right? You could turn it into sine x over sine x. You could turn it into log x over log x. It doesn't matter.
Should you turn it into cosine x over cosine x and converge the 2?
You could turn it over to cosine x over cosine x. Why would that be good if you did cosine x over cosine x?
The same denominator.
Same denominator, you could put those together, couldn't you? So you could either say, let's turn the 1 into cosine x over cosine x, or you could have just said, can't we just get a common denominator and put these 2 together? right? So if I do that, then I have to multiply the top and bottom by cosine. That's a legal move, right? Now, I'm not saying that's going to get us anywhere here, but is it legal? Let's do it. Let's try it. Let's get a common denominator. So if we get a common denominator, limit x goes to pi over 4. Okay, this is going to turn, just so I'm going to put it up here just so we see it. This turns into cosine x over cosine x. And now when we put them together, the numerator is cosine x minus sine x over the common denominator, which is cosine x, but all of that is still over sine x minus cosine x. Do we all believe this? Is that the same thing?
Yep. Yes, sir.
All right, put those two together. That's this, and then over this. All right. That's a legal move. Now what? Anybody see it?
Multiply by the conjugate, and you get your rule, right? Sine x squared x plus cosine squared x equals 1.
Oh, so you want to do conjugate? Conjugate of what? Of this guy?
Bottom, I think.
Of this guy?
I think so.
And then maybe you'll get the Pythagorean identity out of that?
Which equals 1, right?
That might work, actually.
Yeah.
I actually think that might work. I'm willing to go down that road. There's something a little bit cleaner, though.
Since it's a complex fraction, could you flip it and multiply?
You
it
could
by
flip
it?
and multiply as well, right? Would that help, though? Like, if you look at this as this over 1, then you could do fraction over fraction, which is the same as multiplication of the reciprocal. Do y'all see that there's a cancellation here, almost?
Yeah.
Where's the almost cancellation?
Numerators,
This right here and this right here are almost the same. They're off by
negative.
a negative.
Yeah.
So we just pull a negative 1 out and then cancel them. Let's do that. Now, I like that conjugate thing. And we might actually get there that way. I'm not going to go that road just because this is a little cleaner, but I'd be curious if it worked. All right, so cosine x minus sine x over cosine x. I'm going to multiply that by the reciprocal of the bottom, which is 1 over sine x minus cosine x. Okay, that's just me rewriting it. Now we said these almost cancel, right? These almost cancel. I just need to pull a negative out. So what I'm going to do here is I'm going to pull a negative 1 out of the bottom, and that gives me negative sine x plus cosine x, like that, right? So no longer looking at that. That's my new denominator down there. And do they cancel now? They do. They're in different order, but they are exactly the same expression. So these two will cancel. And so what do we have here? We have limit x approaches pi over 4. Okay, this canceled. I get 1 over cosine x times over here 1 over negative 1. Don't forget the negative 1 we pulled out. Let's take the limit. Let's let x go to pi over 4 now. What's cosine of pi over 4? Root 2 over 2, right? And that's not a problem anymore, is it? This is going to be 1 over the square root of 2 over 2 times, that's just negative 1. So flip that fraction, flip this fraction over, and make it negative. Negative 2 over root 2. That's your answer. We actually didn't need either one of these. The way we went in this problem, we didn't need either one of these. Questions?
We're allowed to leave it with the square root at the bottom?
I don't know. Let's see. Let's ask everyone. Am I allowed to leave the square root down here?
Technically, no.
No?
No.
No?
I mean,
Rationally.
logically, you're able to, but some teachers get mad at that.
Yeah.
Some teachers get mad?
Pearson will accept it.
What's that? Pearson will accept it.
Yeah, that's what I really think.
So this drove me crazy as a student because I was told I cannot leave it like this, that you have to get rid of the root on the bottom. And then, of course, as I studied math, I started to realize, wait a minute, it's the same answer. Why can't I leave it down there then, right? So we're going to talk about this, all right? We're going to talk about it right now. So we're done here. Any questions here? We're done? All right, I want to talk about this whole idea, but I want to use a different example. So let's say we're working through a problem, all right, and we get this as our final answer. This actually came up a little bit in pre-cal. Let's say our answer is 1 over root 2. All right? So you want to box that up and say, that's my answer. You're told you're not supposed to, right? You're told, no, you can't do that, that you must rationalize. So you're told that you're supposed to take this and multiply the top and bottom by what? Square root of 2, square root of 2. And when you do that, across the top you get root 2, and then the root 2 times root 2, that just gives you 2. So you get this answer, right? So if you have a calculator, I'd like for you to try this on your calculator if you have it. Did I tell you didn't have a calculator, right, sir? You can, everyone, this goes for everyone in here. If you are in need of a graphing calculator, the college will rent, it's free. We'll let you check out a graphing calculator for the entire semester. You just have to go over to the Math Tutoring Lab, Juniper Hall, room 308, and they will just check your student ID, they'll check you off, and they'll hand you a calculator you have for the rest of the semester. So since yours is the advanced one, you might want to just go check one out. That way you don't have to buy one, okay? That's JH 308. Okay, so if you check on your calculator, these give you the exact same answers. Did anyone try it? What this is a decimal? I can tell you what it is. It's approximately 0.707, all right? Both answers, no matter how, if you do it either way, you're gonna get the same answer. So why was I told that you can't leave it like this, right? If they give you the same exact answer. So here's the reason, because again, it really frustrated me that I was told I can't, right? I mean, I was told I can't, right? Not it's up to you or we don't look, we frown upon it. It was you can't do it, and it was that upset me. So here's the reason why, okay? Here's the reason why. So imagine back there was a time when we didn't have calculators, right? We didn't have just go take the square root of 2, right? Couldn't do it. So these certain numbers came up in math a lot, right? There were, pi, square root of 2, e. These were all numbers that were all over mathematics, all over physics, chemistry, biology. These things would come up everywhere. And we didn't have calculators, so students had to memorize what these numbers were. So if you were back in the 1950s taking math, you would have to know that pi is approximately 3.1415. This is an irrational number. It keeps going forever. There's no pattern to it, never stops, okay? That's an irrational number. Square root of 2 is also irrational. 1.414, it keeps going forever. There's no pattern to it, right? Never repeats itself, just keeps changing. It's weird. And then e is also irrational. 2.718, and it keeps going, no patterns to it at all. So students had to memorize these, okay? They just had to know them. They had to know what they were approximately. And so they used to have like contests, like who could memorize pi out the furthest. And it used to be like a show of like your math prowess, like I know pi, 50 digits. I have a colleague that still works here, still teaches here, that at some point in his life he claims to have known pi out 120 decimals, 120. I was a little skeptical, but on his 60th birthday, okay, his son, who's an engineer, had his wife bake him a cake. I went to the birthday party, and they hid this cake in the back room. He had no idea about this cake. And it was a cake that looked like, it was like this. It was a really long cake. Okay, I'm not making this up, all right? It was a really long, like, brick cake. It was probably as long as this table right here. Maybe half of it, whatever. And they had the little wax candles that are numbers, right? And they had his son put on there, had his wife put on there, pi, okay, out 60 digits for his 60th birthday, right? So a surprise party, he shows up, we've been drinking whiskey and stuff. He was a little bit, buzzing and stuff. And he's like, walks in, he's like, he looks at it, turns around, back to the cake, looking at us, and starts spewing out all the numbers on the cake. And he did it perfectly. And he got to the 60th number, and he looked at his son and said, did you round the last digit or not? So that he could get the last one right. And he got it right. So anyway, they used to have competitions, right? The world record, I believe, is 60,000 digits. It's either 60,000 or 16,000. I don't remember. The guy who stopped, who got the record, he stopped because he was just tired. He could have kept going, but it took him like 8 or 9 hours to do it. It's really interesting if you go and look it up. It's this guy, he's a savant. So he doesn't look at numbers the way we look at numbers. He looks at numbers like scenery. So like if you think about, if you try to describe to me, if you try to memorize 100 numbers right now, that'd be hard. But if I asked you to describe in detail what it's like when you wake up and get out of bed, like you tell me like what's on your dresser, you could tell me on your sink, like where things are, right? You could be very detailed because it's just visual, right, to you? That's the way he looks at numbers. He walks through the number like a scene. It's crazy. So, all right, where am I going? All right, so back to this. They had to memorize this, right? No calculators. So, imagine now you get to this answer right here. And we need to get the decimal approximation to this, and you don't have a calculator, but you have memorized what the square root of 2 is, all right? Got it? So if I do this, then what I have to do to figure out what this is long division. Good old school long division. I take the one that's on the top. On the outside, I do the square root of 2, which I've memorized to be about 1.414. That's not right. 1.414, not 1.14. 1.414, right? So now I have to do this division. So I have to ask myself, how many times does 1.414 go into 1? Shit, I don't know. Right? It's hard. It's hard to think. I don't know, right? It's not obvious to me, right? Now, if I rationalize it first, right, and do it this way, now what goes in the division box? The 1.414. And what goes on the outside? The 2. Now this I can do because 2 doesn't go into 1, right? So I bring my decimal point up. 2 goes into 14 7 times, and then I carry on. See, the number on the outside is a nice integer, as opposed to over here, it's an irrational number. It's harder to do that division. So I could carry on. This is 707. It keeps going. Do you see how that's just easier to do by hand? And it's obsolete, right? This is obsolete at this point. We don't need this, right? We have a calculator. So you never have to. In fact, if you ever get a root on the bottom, I almost want you to leave it like that, almost as like a, like kind of an FU to everyone who told you couldn't do it, right? Now, the actual idea of rationalizing is not a bad idea. Like the technique of rationalizing is something you should know about. Like you can multiply top and bottom by a root to make the root go away on the bottom. That's a good technique, but you can't say that you can't leave a number that way, all right? That's why your computer online system will take that answer. Is that what you were saying? Who said that? This computer would take that answer, right?
On Pearson?
On Pearson, yeah, like on those systems online, if they'll accept that answer. Okay, we got to move on. So we are done with this section. I would like for you to go ahead and complete the problems after. Whoa, stop. Where were they?
49 to 54.
Yeah, really 49, is it 49 to 54? Let's just say that's it, okay? Problems 49 to 54. 1.4. And look, those problems, just turn them in with your next assignment, okay? You don't have to resubmit a new one. Just your next assignment, throw those in there. I have not looked online today to see if everyone uploaded their handwritten work. I'm still working on my other classes that submitted a couple of days ago. When I do look at them, I'm just going to be looking like, does it look nice and clean, and does it look like you made an honest effort at this? So I'll update those grades hopefully today. All right, questions? 1.4, we're done? All right, we've got about 40 minutes to do the next section, 1.5. So we're going to now talk about, this is actually a really, really important idea in this class, but it's one of those ideas that I'll mention it as we move through the class, but what we're actually going to do like mechanically by hand today is something that we're just going to see it, do it, put it away, pack it, and not mess with it anymore, all right? So the idea is this. We have this thing called continuity. continuity. So we've been talking about a function, right? We've been talking about limits. Now we talk about this thing called continuity, and I'm just going to make it real simple for us to start out. If I look at the graph of a function, if I can draw it without picking up my pencil, then that is what we call a continuous function. So if I take some function, I draw it, let's say I just go from here to here, let's say I stop there, start there. This would be an example of a continuous function. I draw it without picking up my pencil, right? There's no breaks, right? No breaks in the graph. No jumps. No vertical asymptotes. Etc. All right? It's nice. I just draw it without picking up my pencil. That is what a continuous function is. Just like the layman's version of it. If you're trying to explain this to like a college algebra student, that's the definition. All right? Yes?
If it goes on for infinity, is it still continuous?
Sure. As long as it doesn't have a break or a jump, just then it would. So the question was, if you didn't hear, what if this was an arrow and just kept going? Then yes, it would still be continuous as long as you can say that you never picked up your pencil. All right? You could have this would still be continuous, right? Look at this one. You could have this sort of thing. Well, you have to be a function. You can't fail the vertical line test. Okay? That would also be a continuous function, right? There's no breaks, no jumps, I'd never picked up my pencil, right? Still passes the vertical line test. So that is a continuous function as well, all right? So what are some things that wouldn't be continuous? Look at this right here. So if you want, put a check mark under that, that's continuous. So here, how about this function? Say it goes down forever. So far, so good, right? Okay, right here, I'm going to put a hole, jump up, and go like that. Not continuous at a particular point. Everywhere else it is, though, right? Like over here, I didn't pick up my pencil over here, right? I don't have to pick up my pencil here. There was only one place right here. Let's call this value a. At x equals a, right, I'm not continuous. Right? Why? There's a jump, right? There's a jump. There's a break in the graph. I had to pick up my pencil. Do y'all see that? So I would say here that this function, let's say we call this function f. I would say that this function f is continuous everywhere except at x equals a. Right? Everywhere except here. Let's do another one. How about this? So far, so good? Okay. How about that? Not continuous at a single